Do you teach finite elements using MATLAB or?
Lately, I haven't, just because there hasn't been that much of a, I haven't really gotten, I think people would rather focus on the ANSYS. And so I teach a lot more on the ANSYS side than MATLAB. I do have some stuff prepped for MATLAB, but I mostly say that for my grad students now, like grad student finite element classes. Is Dr. Park teaching virtually now? Because usually he's in here before me, but.
He's from last time we heard, he was at a conference in Hawaii.
Oh, interesting. Okay.
Yeah, he wasn't gonna come back till the 11th. At first, we thought it was a typo, but then he showed up Monday and there was nobody in here, so we were like, oh, looks like it was true then.
I see.
The professor to the heat waves concerning.
The heat waves?
It's gonna be like 63 in 3 days.
I know. Yeah. It's like that. You have to be prepared for like freezing weather and like super hot weather nowadays. It all happens in the same week now too. It's crazy times.
Yeah.
What's up?
What What's the name of the class that you teach to simulate a flow using method?
It's 442, and so it's called computational cardiovascular engineering.
Is it spring or fall? Or-
It's still, it hasn't, it's not a full course yet. And so usually when a new course comes up, we teach it first as we call it a special course.
Mhm.
And so it doesn't have a set schedule, but I've taught it the last 2 springs. And usually we don't offer those tech electives more than once a year. So I think probably next time I'll offer will be next spring. Hey, guys.
It's hot today.
I know. Ooh. Weather keeps changing and changing.
It's a lot.
A little bit. We'll be talking about that actually at the end of the class.
Radiation.
Radiation in general. So not today, but end of the semester.
Right. After the midterm?
Yeah, after the midterm. Hey, how's it going? Good.
All the time?
Probably there for the, I got classes at 8:30 tomorrow, so probably not super late, but
Let's leave over there.
yeah, seriously.
All right, it's 2:30. So let's go ahead and get started. Good afternoon, everyone. How's everyone doing today? Doing good, doing good. We're end of week 11. So, we're getting right up at the end of the semester. Okay, so the plan for today is we're going to finish up our lecture notes on free convection And then that'll probably take about half the time today. And then we're going to start a new set of lecture notes on heat exchangers. And heat exchangers kind of marks the end of this unit. And so this whole unit kind of has the theme of convection. And so after we're done with heat exchangers, then we're going to move on to radiation after that. Okay. All right. And so some announcements I have to make. I know Monday, I was thinking about changing the midterm date. And so I said I would put out a poll. But I thought, I'm just going to make an executive decision. And so I pushed the midterm back. So the midterm is going to be now on Monday, April 25th. And so that is about 19 days from now. Okay. So the reason I did this is because I do want to get one more homework assignment in before the midterm, because, as you can see from homework 5, it only covers up to internal convection. But I want to give you guys some practice with free convection and heat exchangers before the midterm. And so if I had the midterm on 4/20, then I would have to make the homework 6 due, just a week after homework 5, and then you would have to take the midterm the 2 days after that. And so, that was a little bit too short of a time window. And so I decided to push it back to Monday, just so you have a couple extra days for homework 6, and you have kind of an extra weekend that you can study for the midterm. Okay. And so I think hopefully we'll finish up all the heat exchanger stuff by next Wednesday. And so that should give you, a week after we finish heat exchangers to do the homework on heat exchangers. Okay, so that's the plan for the next couple of weeks. And then after homework 6, I only have one more homework for the class. And so I just have one homework for radiation planned. And then after that, then we'll start preparing for the final exam. Okay? So it's going to go fast. And so it's going to be kind of like bang, bang, bang up until the final week. And so, I wanted to get you guys some dates beforehand just so that you can kind of plan ahead for the next few weeks. All right, and so that's it for my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. And we are talking about free convection. Right? I think this is day 3 of us talking about free convection. All right, and so we all know what free convection is at this point. So free convection occurs basically whenever you have a temperature difference in a still fluid, right? And so that's the key. And the main driving force behind free convection is the fact that when you heat a fluid or when you cool a fluid, its density changes. And when a fluid's density changes, it tends to rise and fall when you compare that density to the density of the surrounding fluid. Okay. And so we basically have buoyant forces. Okay, which are caused by temperature differences. Okay. All right, so that's the basic principle behind free convection. Right? And so we've only really looked at just one situation so far. And so the only situation that we've looked at so far in our examples and in our derivations has been a heated plate in a cool fluid. Right? Right? And so we know what's going to happen in this case is the hot plate is going to heat up the fluid next to it. And as the fluid next to it gets heated up, it's going to start to rise, because as fluid gets heated up, its density tends to decrease, right? And as the density decreases, it's going to want to rise to the top when it's surrounded by more dense fluid around it. Okay. So today I wanted to look at some other situations that can occur, because there's a lot more out there than just a heated plate in a cool fluid, right? And so let's look at the opposite situation. So let's say that we have a cold plate. Okay. And surrounding it is some relatively hot, still fluid. Okay. I use the terms hot and cold just to basically denote which one has higher temperature, right? And so on the left right here, we have if the surface temperature of the plate is Ts and the fluid temperature is T infinity, on the left right here, we have Ts is greater than T infinity. Okay. If we use the same notation on the right, and so we call the plate temperature Ts, and the fluid temperature T infinity, the only thing we have here now is that TS is less than T infinity. So it's just the opposite. It's not that it has to be significantly colder or, or the fluid doesn't have to be boiling hot. It's just that you just reverse the sign, or, reverse which one is hotter or cool. Okay. Right. And so by the same logic, if we kind of go by that logic of, when you cool a fluid down, or as the temperature of the fluid decreases, it gets more dense, then you're going to have fluid flow that goes in the opposite direction in this case. Okay. And so on the right case, because the solid temperature is lower than the fluid, it's going to cool the fluid down next to it. And that cooled fluid is going to want to sink. Right? It's going to go in the direction with gravity because it's more dense. Okay. Okay. And so that's kind of visually what happens. And so, I think the next question that you can ask is, how does this affect what we do? Okay. And so how does this affect our Nusselt correlations? So do we have to, know a different set of Nusselt correlations for this? How does it affect our convection calculations? Okay. And so you would think there would be a difference here because, the fluid is going in a different direction. Right? And so I would say that's true from a fluid mechanics perspective. And so from a fluid mechanics perspective, there is going to be a difference. The fluid's going in the opposite direction. And so you're going to have a different kind of boundary layer formation. You're going to have a different, different edge effects, right? But in terms of heat transfer, it actually doesn't make any difference at all. Good. And so whether you have a cold plate or a hot plate, you can still use the exact same Nusselt correlations, given that it's a vertical plate, right? And so as long as you have a vertical plate geometry and fluid is going down kind of parallel to that plate, whether it's going up or going down, it's still not going to make a difference from a heat transfer point of view. And so you can use the exact same relationships and the exact same formulas that we used, from the previous two examples that we did in the last lecture. Okay. And so I bring that up because, it's something that, I think a lot of people kind of wonder, because the examples were kind of lopsided up to this point. So we've only just done a hot plate and cool fluid, but, I just want to let you know that, no matter if you have the opposite situation, you still can use the exact same formulas, given that you have a vertical plate geometry. Okay. Okay. I make that disclaimer because, we're going to cover a new geometry next. And so, I want to emphasize that this only occurs for vertical plates. Okay. Any questions on this? Okay. All right. So that's vertical plates. And so we've covered basically everything that we need to for that. Now let's go over kind of the another geometry. And so let's go over horizontal plates. So this is going to be horizontal plate free convection. Okay. So this we have to account for some other things, and so I'll kind of show you what I mean with that. And so I think the easiest way to illustrate this is with a picture. Right? Let me draw two plates here. These two plates aren't next to each other, and so these are kind of two separate situations. And so on the left here, I'm going to have a hot plate. Okay. And all hot just means that the plate is a higher temperature than the fluid around it. And on the right here, I'm going to have a cold plate. Okay. And we'll assume that the fluid temperature is the same on top and bottom of the plate. So we have T infinity down here, T infinity up here. Okay. Just for the sake of simplicity. Okay. All right. And so let's draw what we expect the fluid to do, you know, we have kind of four situations here. And so we have the situation on top of the hot plate. We have the situation on the bottom of the hot plate. We have the situation on top of the cold plate and on the bottom of the cold plate. Okay. All right, so let's look at the hot plate conditions first. And so let's look at the top left. Okay. And so we know that as fluid is heated up, then it's going to want to rise, right? And if we assume that gravity is pointing downwards, you know, as we usually do, that means if we look at the fluid on top, you know, the fluid is going to want to go up, right? Right? Okay. What's going to happen on the bottom of the plate? And on the bottom of the plate, you know, the same thing is going to happen on the top, right? And so we're going to have the hot plate is going to heat up the fluid. And so the fluid's going to want to rise, okay? And so we're going to have fluid going this direction again. Okay. And so in both cases, we have the fluid is rising up, right? So the fluid's going in the vertical direction. But there is a difference of what's happening on top and the bottom, right? And so let's look at the top situation, right? And so on the top right here, you can see the fluid one's going to want to rise up, but which direction is it going to? Is it going relative to the plate, right? And so as the fluid rises on top, there's no solid surface on top. And so what we can say is that on top right here, the fluid rises away from the plate. My iPad's first right now. Okay. On the other hand, if we look at what's happening on the bottom, right, the fluid is rising, but it's rising back towards the plate. Right. And that distinction is going to be really important, you know, which we'll talk about in a bit. Okay. All right, so now let's do the cold plate example, right? So as opposed to the hot plate, you know, cooling down the fluid is going to want it to sink, right? And so we're going to have on top right here, the fluid is going to want to go down. And on the bottom here, the fluid is going to want to go down as well, okay? So we're going to have fluid falls, okay? But because the fluid's going in the opposite direction, we have a different, you know, direction towards and away, right? And so a cold plate, if you look at the fluid on top, the fluid is going to fall towards the plate. Whereas the fluid on the bottom of the cold plate falls away from the plate. All right. So why am I making such a big deal of whether the fluid's going towards or away from the plate? Well, it makes a big difference in terms of the fluid mechanics, right? Okay. And I'll draw what some of those fluid patterns look like in just a second. But more importantly for us, you know, because this is a heat transfer class, you know, we care about fluids, but you know, we only care about it as much as we have to. But whether the fluid's going towards or away from the plate, that's going to change which Nusselt number correlations that we're going to use. Okay? Okay. And so you'll see that, we'll have different formulas for the Newton number, whether the fluid's going towards or away from the plate. Okay. And so when you look at this, combined together with kind of the first point that we went over today, free convection doesn't really care all that much whether you have, you're heating up the fluid or you're cooling it, right? What does matter is kind of what the fluid velocity patterns look like around the plate. Okay? So that's what's actually going to make an impact on your heat transfer, not necessarily whether the plate is hot or cold. All right, any questions on this? Okay, so let me just draw really quickly what the fluid flow patterns look like, just so that you can kind of get an idea. Okay, so let me draw the two cases here again. So we have a hot case and a cold case. And so for a hot case, we know that the fluid's going to want to rise. And so if you trace out the velocity patterns, they look kind of something like this. And so, first fluid's going to come in, right? Fluid's going to come in from here. It's going to get heated up, and then it's going to want to go up just like that. Okay. Fluid's going to come in, it's going to heat it up, it's going to go away from that. Okay. Fluid's going to heat up and it's going to go away. Okay. And so what you can say in the end is that when you're kind of forcing the fluid to move away from you, then you have a bigger net flow outwards away from the plate. Okay. And so what you can say is that, when fluid moves away, there's more bulk transport away from the plate. And if there's more bulk transport, then what we expect is that there's going to be more convection occurring in that case. Okay. Right. And so what you'll see is that for flow away from the plate, you're going to have a higher Nusselt number than flow coming towards it. Okay. All right. And so that's the situation when flow goes away. Now let's look at what happens when the flow goes towards the plate. And so when flow goes towards the plate, we're going to have flow that comes in here, right? But then as the flow, it wants to keep rising, but then the plate kind of gets in the way. And so once the fluid kind of hits the plate, it kind of bounces off and kind of goes to the side. Okay? And you're going to have flow that comes in, bounces to the side. Flow that comes in and bounces to the side. Okay? Because there's nowhere for it to go. And so, it can't keep rising. And so the only option for it is to kind of just deflect and kind of move off to the side. Okay. And so when flow goes towards the plate, there's still a net flow. And so, the fluid is still moving, but the fluid kind of gets, it kind of just moves kind of parallel to the plate and kind of gets stuck there. Okay. You can say the fluid okay, because it wants to keep rising, but the plate's just kind of in the way. And then the opposite, and so the opposite, you can draw the opposite patterns for the cold plate as well. And so for the cold, we know if we're looking at the fluid on top, the fluid's going to come in, it's going to hit the plate, it's going to deflect to the left and the right. Okay. Okay. Meanwhile, the fluid on the bottom is going to move away from the plate. Okay. And so if you want to maximize heat transfer, or if you want to see, you know, which one is going to have more heat transfer than the other one, then the away cases are going to have bigger, you know, more heat transfer. Any questions on this? Okay. All right. So then let's actually put some formulas to this. And so, you know, let's list out what the Nusselt number correlations are. All right, so let's look at first the situation when we have fluid going towards the plate. Okay, hot or cold, it doesn't matter. And so we have fluid going towards the plate. Our Nusselt correlation is the following. So we have Nu is equal to 0.52 times the Rayleigh number raised to the 1/5 power. Okay. And this is valid. This is valid when the Rayleigh number is between 10 to the 4th and 10 to the 9th. Okay. Next, we have a situation when the flow is going away. And so in this case, the Nusselt number is equal to 0.54 times the Rayleigh number raised to the 1/4 power. Okay. And so you can see right away that the exponent on the Rayleigh number is much, well, it's not much larger, but it is larger going away, right? And so instead of a 1/5, you have a 1/4. Right? But actually, that actually does make a big difference in terms of the Nusselt number that you compute, because it's an exponent. All right. And so this Nusselt number correlation is valid when the Rayleigh number is between 10 to the 4th and 10 to the 7th. And so you can kind of almost think of this as like the laminar version. And so when the Rayleigh number exceeds that for away, we have another Nusselt number correlation. Okay. And so this one is 0.15 times the Rayleigh number to the 1/3 power. Okay. And this is valid when the Rayleigh number is between 10 to the 7th and 10 to the 11th power. Okay. And so when you have much higher Rayleigh number, you know, you basically have turbulent flow, then you're going to have a much higher Nusselt number as well. Yeah, question.
So if we do get something that's near 10 to the 7th, we could still use it for the first away that we did.
Yeah. Yeah. And so if you're around 10 to the 7, that's kind of like the transition area. And so you can kind of go either way. And so I would probably err more on the left side, but that's kind of rare to have one that kind of straddles that threshold. Okay. One more thing I want to talk about before we do an example. And so, you know, when you compute the Rayleigh's number, you need the length, right? Okay. You would think that, you know, if we have a horizontal plate like this, you know, we would use this length right here, right? So you would think that we would use the horizontal length of the plate. You guys have a question?
The third correlation. 10 to 7 to.
Oh, 10 to the 11th. The other one's 10 to the 11th. Yeah. Mhm. And so you would think that, you know, when you're plugging in for the Rayleigh number, the length that you choose would be the horizontal one, but that's not the direction that the fluid's going. Remember, the fluid's going up and down, right? And so it doesn't really make sense to use the horizontal length of the plate. Right? Okay. Instead, you know, we're going to tap into, if you remember when we did this with the Biot number, we're going to tap into something called the characteristic length. Okay. right? And so the length that you use should be the area or the area of the flat plate divided by its perimeter. Okay? All right. And so you'll see what I mean, once we do an example of this, it'll be a bit more clear. All right, any questions on this before we jump into example? Yep. Yeah, so if the railing numbers are outside those ranges, then it depends. And so if you're below that range, and so if you have a railing number that's less than 10 to the fourth, I would say that you're probably in a situation where the temperature difference isn't big enough to cause any free convection. And so you're probably in a situation where you can kind of ignore it. And so if that's the case, then and if the fluid was still, I would just treat it as like a pure conduction situation. And so the heat would just be purely conducted to the fluid. If you're above this range, if you're above 10 to the seventh, then you might be in a situation where radiation actually becomes more relevant. Because remember, the big thing that drives the Rayleigh number up and down is the temperature difference, right? So the difference in temperature between your solid and your fluid. And so this is jumping ahead a little bit, but you'll see what we'll see in radiation, because radiation doesn't go as T minus T, it goes as T to the fourth minus T to the fourth. And so the bigger your temperature differences are, then radiation is going to play a much bigger role. And so if your temperature differences are so big that your Rayleigh number is greater than 10 to the 11th, I'd say that's another situation we could ignore free convection, but we treat it as a radiation problem instead. Yeah. Mm-hmm. Okay, all right, so let's do an example. All right, so in this example, let's say that we have a rectangular duct. Right, and this is filled with stagnant air. All right, so here is the cross section of the duct. Okay. And we're going to assume that the duct kind of goes into the page just like that. Okay. All right, and so inside this box here, we have air. Okay. Let me give you some dimensions here. And so let's say that this length right here is L, and this is equal to 0.75 meters. Okay. This length right here, we'll call it the height for H, is equal to 0.3 meters. Okay. The surface temperature of the duct, or in other words, all the walls of the duct, we're going to assume it's the same temperature, right? And so we're going to assume that this duct surface temperature here is 45 degrees C. And inside the duct, we have air, and we're going to assume the air is at a much cooler temperature. And so we'll assume that air is at 15 degrees Celsius. Okay. And just for the sake of simplicity, we're going to assume that the length of the duct in this direction is going to be 1 meter. All right. And so what we want to do in this problem is we want to compute the heat loss from the duct to the air. Okay. Right, and so since we're looking for heat loss, what we're ultimately looking for is Q, right? And so we're going to have 1 Q that's going to be in units of watts at the end of the problem. All right. So this is an interesting one. And so, we have a duct right here, but we haven't studied ducts yet. So, we don't have the geometry for this. But let me take this duct and let me break it down for you. And so first, let me circle these two, the vertical sides of the face, okay? If we take those two in isolation, right? And so if we say that this is a side of the duct, and it has a length of h, okay? Give it a little bit of thickness too, okay? What you'll see is that this is basically a vertical plate. Right? And so the two sides, the two vertical sides of our duct, we can treat them as basically vertical plates. Okay. On the other hand, if we take the top and the bottom of the duct, right? And so this length is, oh, I used L twice. So that this L doesn't really matter, called L2 there. Okay. And so we have a horizontal plate that's length L, okay? And I just kind of said it, but basically we have a horizontal plate. Right? And so even though it might seem like, we're kind of ill-equipped to do this problem, if you kind of break up the geometry into parts like that, we actually have everything we need. The only downside to this is that, because we have a rectangular duct, we kind of have to do four free convection calculations at the same time, right? Okay. So this is a really nice problem to end on because it kind of gives us a lot of practice kind of going over everything that we've gone over with free convection. Okay. All right, so let's go ahead and get started. And I kind of glossed over it, but the fact that we have stagnant air here means that we're going to treat this as a free convection problem. But if you had some kind of velocity, then you would have to compare whether forced convection or free convection is going to be more relevant. But because the problem stated from the beginning, we have stagnant air. This is kind of the key word that tells you that we're doing free convection. But that's also kind of obvious just because we're still in a free convection motion. But that logic is important to point. Okay, so we're going to do our convection problem-solving methodology, just like we usually do in these problems. Okay. Step one is we're going to identify the situation. Right, and we have to do this 4 different times, or really it's 3 because we have the 2 vertical plates the same. Okay, and so the one hand we have 2 vertical plates. Okay, and so those are going to be the two vertical sides of our duct, right? And so this will be, we'll call that part A. B, we have one horizontal plate. So let's do the top one first. Right. And remember, when we talk about horizontal plates, we need to describe whether the fluid's going towards the plate or away from the plate. Right? And so in this case, we have a hot plate where the fluid is below it, right? Because the horizontal plate here is on top, considering this one first. Right? And so if we have a hot plate and cooler fluid below it, then the fluid's going to go towards the plate, right? Right. And lastly, we have the bottom horizontal plate, okay? And so here we have the opposite situation where we have a hot plate, right? But the fluid is instead above it. And so what's the fluid going to do? It's going to go away from the plate, right? Because it's going to want to rise away from it. Okay? All right, so those are the three situations that we're going to need to solve for. We can solve for the two vertical plates. We can just do it once and then we'll just multiply by 2 because it's the same. All right, step 2 is we need to specify our reference temperature or our film temperature and compute the fluid properties. Okay. All right, and so our film temperature here, TF, is going to be the average between our two temperatures. And so our duct is at a temperature of 45 degrees C. The air is at 15 degrees C. And so we just take the average. We end up with 30 degrees C. Okay. And remember, for free convection problems, we need to compute our parameter beta, right, which is our thermal expansion coefficient. And so we need to take this 30 degrees C and convert it to Kelvin as well. Okay. And so to convert temperature from degrees Celsius to Kelvin, we just have to add 273. And so that's going to give us 303 degrees Kelvin. Okay, and so if we look up the fluid temperatures at this fluid properties at this temperature, we have the viscosity, and so the viscosity is 16.2 times 10 to the minus 6 meters squared per second. We have our thermal conductivity, Kf, is equal to 0.0265 watts per meter Kelvin. We have our Prandtl number 0.71, and our beta. Remember, the way we compute beta is we take the inverse of the film temperature, and so we're going to take 1 over 303, and that's going to be 0.0033 Kelvin minus 1. Okay. All right. So that's step 2. So now that we have our fluid properties, we're set to compute our correlations, right? And so the first step, before we compute our correlations, is to compute our Rayleigh numbers. Okay. And so we need to compute 3 here. Okay. So let's start with the vertical plates. All right, so for the vertical plates, this is pretty easy. And so our Rayleigh number is going to be equal to gravity times beta times the temperature difference, Ts minus T infinity, times the length of the plate squared. But remember, the vertical plates, the length of that plate is h, right? And so I'm going to multiply by h cubed. Okay. All divided by the viscosity squared, multiplied by the Prandtl number. Okay. All right, so we go ahead and plug everything in. We get a Rayleigh number of 7.07 times 10 to the 7th. Okay. And if you remember, for vertical flow, our vertical plate flow, then our magic number here is 10 to the 9th, right? And so if we go above 10 to the 9th, then we're turbulent. But if we're less than 10 to the 9th, then we have laminar flow, right? And so here we have 7.07 times 10 to the 7th. Since this is less than 10 to the 9th, then we have laminar flow. All right. So that takes care of the 2 vertical plates. Okay. Now let's take care of the horizontal plates. So we can do them together because the Rayleigh number is going to be the same between the 2 horizontal plates, but eventually they're going to be plugged into different correlations. Right? And so we can do B and C together at the same time. Okay. And so just like the vertical plates, we have our Rayleigh number. It's going to be equal to G times beta times Ts minus T infinity multiplied by length cubed divided by viscosity squared times the Prandtl number. Okay. But remember, when we have horizontal plates, we don't just plug in the length, the horizontal length of the plate straight up. Okay. And so what we're going to plug in here is a characteristic length. Remember, the characteristic length LC is equal to the ratio of the area of the horizontal plate divided by its perimeter. Okay. And so with that in mind, let me go back to the problem geometry above, just so we can see what the area and the perimeter should be. Okay, so here is our geometry here, right? Our horizontal plates in question are these plates right here, right? And so we have this plate on top, and we have this plate on the bottom right here. Okay. We know that one edge of this rectangle has a length of 0.75 meters. And then the length into the page of that is going to be 1 meter right here. Okay. And so if I take that plate and kind of rotate it up so you can see it this way, that rectangle would look like the following. So we have a plate that looks like this. And so this length would be 0.75 meters. And this length right here would be 1 meter. And so you can think of this is like a top view or a bottom view of our plate. Okay. And so with that in mind, we can compute LC. So LC is going to be the area, or we start with the area. And so the area here is going to be just 1 meter multiplied by 0.75 meter. Okay. And we divide by the perimeter. And so the perimeter here is 2 times 0.75 plus 2 times 1. Okay. And so we compute all that, we get a characteristic length of 0.214 meters. All right, so let's take that characteristic length. Let's plug it back into our formula for the Rayleigh number here. Okay. And if we do that, then we get a Rayleigh number, which is actually pretty close to the threshold. We have one that's 3.64 times 10 to the 7th. Okay. And so now that we know the Rayleigh numbers for both the vertical plates and the horizontal plates, we'll be able to pick the correct neutral number correlation to go with them. All right, any questions on this? Oh. All right, question. So can I explain again why the top horizontal plate is towards and the bottom plate is away? Yeah, sure. And so for this problem, we basically have a hot duct, right? So the walls of the duct are 45 degrees C, whereas the fluid here is only 15 degrees C, right? And so if we draw the top plate, right, so the top plate looks like this. Actually, I'll draw both here, okay? Because the fluid's kind of sandwiched in between them. And so here we have the top plate. Here we have the bottom plate. And we know that these plates, both of them, are hotter than the fluid, right? And so whenever you heat up fluid, it's going to want to rise up, right? So all the fluid inside the duct is going to go towards the top. because the fluid's heating up and it's getting less dense, right? And so if the fluid's going up, then for the top plate, the rising fluid is going to go towards it, and so it's going to kind of hit against the top plate and kind of scatter to the left. Whereas from the bottom plate, the fluid is going to rise up and go away from it. Does that make sense? Great, awesome. Okay, so now that we know the Rayleigh numbers, we can go ahead and compute the Nusselt numbers. And so we have three that we need to compute here. And so let's go with the vertical sides first. Okay. Remember, based on our Rayleigh number here, we have laminar flow because it's less than 10 to the 9. Okay. And so our Nusselt number correlation here is 0.59 times Rayleigh number to the 1/4 power. Okay. So that was from the last lecture. And we compute that, that's equal to 54.1. Okay, next, we have the top plate where the fluid's going towards it. Okay. And so here we have our Nusselt numbers equal to 0.52 Rayleigh number to the 1/5. Okay. We plug in for that, we get a Nusselt number of 16.91. All right, finally, with the bottom plate, we have fluid that's going away. And the Rayleigh number is greater than 10 to the 7th, okay? And so for these ones, we have Nusselt numbers equal to 0.15, Rayleigh number to the 1/3 power, okay? And what you get from this is 49.71. So a lot of plugging in. If your calculator, if there's one thing that happens a lot in convection, your calculator gets a good workout, and so there's a lot to plug in. But these are what you get. All right, so we're almost done, and so now that we have the Nusselt numbers, we can go ahead and compute the convection coefficients. And so let's do the lateral walls first, or the vertical walls. And so we'll call this HA. And so HA here is going to be KF divided by the length of that vertical plate, which is H, okay, multiplied by its Nusselt number. And so if we run the calculations, we get 4.78 watts per meter squared K. Okay. For the top plate, we'll call this HB. Okay. This is going to be KF divided by LC. Remember, LC is our characteristic length, and so don't forget about that. And so we plug in for this, we get 2.09 watts per meter squared K. Right, and finally, for the bottom, call this HC. We have KF divided by LC times the Nusselt number. Okay. We plug in for this, we get 6.16 watts per meter squared K. Okay. All right. So now that we have the convection coefficients, then now technically the convection problem solving methodology is done, but we can then use these convection coefficients to compute heat transfer, okay? And the way that we compute heat transfer from convection coefficients is Newton's law of cooling. And so we have Q is equal to HA times the temperature difference, Ts minus T infinity. Okay. And so we'll do this kind of piece by piece, just like we usually do. Okay. And so we'll do from the vertical plate first. And so for the vertical plate, we have QA is equal to HA times big A, Ts minus T infinity. Okay. HA we've already computed up there. The only thing that's tricky here is the area, right? And so remember, the area is the surface area of that vertical plate, right? And so the surface area for this is going to be H, right? That's going to be one length, and we're going to multiply it by the length of the duct going into the page. So it'll be HL2, okay? And so I believe H was 0.3, and then L2 was 1 meter, because it went 1 meter into the page. All right, so we compute this. We get a heat transfer rate of 43.02 watts. Okay. And so 43.2 watts, that's the heat transfer from one vertical plate, but we have two of them here, right? So we have both the left and the right wall. So we're going to multiply this by 2. And we get a heat transfer rate of 86.04 watts. All right, next we have the top plate, okay? And so this is equal to HB times the area, Ts minus T infinity, okay? So HB we computed up there, but once again, be careful with the area here. So the area here is going to be L times L2, which is 0.75 meters times 1 meter. Okay. Right, and so we compute that, we get a heat transfer rate of 47.025 watts. And then finally, we have the bottom plate. This is going to be HC times area times Ts minus T infinity. Okay. This area here is the same as the top plate, and so you can use the same one for that. And from this side, we get 138.6 watts. And if you go back to the original question, it asks us, what's the total amount of heat transferred? Okay. And so the total amount of heat transferred is just going to be the sum of all of these quantities. Okay. And so if you add up these three numbers, what you get is 271.67 watts. And that there is our final. Yeah.
Does this account for all 6 phases of the?
It accounts for 4 of them. And so we're assuming that the front and the back sides of this are open, because this is a duct with air flowing through it. And so we've only considered just the walls that are surrounding it. Yeah. Mm-hmm. This is a good one. I like this problem. It's one of the good final examples that we can do for this unit, because I think it kind of pulls everything together. Yeah. All right, questions from the chat. So do the corners matter since some of the plates overlap? That's a great question. And so, that is one thing we kind of glossed over here. Normally, when you have horizontal plates and vertical plates, up to this point, we kind of assume that the fluid kind of moves past it kind of freely, like that, right? Of course, here we can't have that because we have corners, right? And so when the fluid flows past the vertical plate, it's gonna hit the top plate and kind of move that way. And so absolutely, it does make an impact here. But for this case, we kind of neglected it. But yeah, but in real life, there are corner effects that you have to account for. Yeah. Mhm. All right, any final questions on this example here, or free convection in general? Okay, all right, so that's it for free convection. Right, and so now we're going to move on to the next topic that we have, the final one in our convection unit, which is heat exchangers. And so if you remember from our very first unit on conduction, we did a unit on fins, right? And it was kind of a, I don't want to say strange, but it was kind of different than the other units, other chapters that we did, because a fin is a kind of a very specific kind of engineering structure, engineering device. Heat exchangers are kind of the same thing. And so, heat exchangers are devices that are, engineering designs that happen a lot in practice, so much so that it actually warrants its own chapter in a heat transfer textbook. And so you'll see heat exchangers basically in any situation whenever you need to exchange heat between two fluids. And so, you'd be surprised, there's a lot of situations or a lot of cases out there where you have heat exchangers, and we'll go over a lot of those situations. And so, because the heat exchanger unit, because it's a lot more applied, there are a lot more equations. And so I haven't let you guys know yet, but I do have I call it like a convection summary sheet. And so I kind of summarize all of the convection unit because, there are just a ton of equations here with convection. And so I'll post that onto the weekly page for this one, just so you can see. And you'll see heat exchangers actually takes up, by itself, kind of a good chunk of that summary sheet, just because there's a lot of equations with heat exchangers. And so, as we're going through these heat exchangers, I don't want you to get bogged down too much with the equations, because it's very easy to do, just based on how many are out there. But I want you guys to focus more on, what heat exchangers are and kind of the conceptual, kind of the intuitive understanding of them, because ultimately that's what you're going to take away from this class. It's not a huge list of formulas. It's, do you know what a heat exchanger is and how it works? Okay, so let's go ahead and start here. So heat exchangers, heat exchanger is kind of a general term. And so what it is a specialized device or specialized application where you have two fluids that transfer heat to each other. Okay. All right, and so in essence, the heat exchanger looks something like this. And so, we have a device like this. Okay, in the middle of the device, you have some very thin wall. Okay, and up here you have a fluid. So we'll call it fluid 1. And on the bottom here, you have fluid 2. Okay. And in order to maximize the amount of heat transfer between them, these fluids are going to be flowing. Okay. And in fact, most of the time the fluids have to be flowing because, the fluids that get transferred heat, or once the heat transfer occurs, then that fluid usually has to go somewhere else to do something important. Okay. Okay, so the two fluids are going to be flowing. They don't necessarily have to be flowing in opposite directions, but here I just kind of did that. Okay. And based on the temperature differences between the fluids, you're going to have heat that gets transferred from one to the other. Okay. Okay, so we'll call that Q. Okay. All right, so basically, you know, in essence, what you have here is we have two internal flows, right? So we have two internal flows of fluid, and they're run, you know, very close to each other, right next to each other, such that they can exchange heat. Okay. And so, what are some examples of this? And so, what are some applications of heat exchangers in practice? Okay. So one of the most common applications of heat exchangers that you'll see is in HVAC. So that stands for heating, ventilation, air conditioning. Okay. We could use a little more air conditioning today. I'm like kind of sweating up here because it's so hot. Okay. And so that's a common application because, you know, in any of those cases, you're either trying to heat up air or you're trying to cool down air, right? And so a lot of times that's accomplished through a heat exchanger of some kind. Okay. All right, another common application is refrigeration, which I always spell wrong. Okay. And so refrigeration, you know, very similarly, you have to transport cold air of some kind into a refrigerator, right? And so that's usually accomplished through a heat exchanger. That's just the most efficient way to do it. Okay. Okay. Another application is radiators, and so you have radiators in the car, right? And so that's also another device that's used to, you know, transfer heat between two fluids, right? So that's a very common application. Okay. And you see it a lot in power production as well. So anytime you have power plants, chemical plants, you know, those kinds of applications kind of, they need to offload a lot of heat. And oftentimes the most efficient way to offload that heat is through a heat exchanger of some kind. Okay. And so oftentimes the power production facility, you know, it produces heat, then that heat is offloaded to a fluid, and that fluid passes it to another fluid, which is safer to kind of expel into the environment. Okay. And so the common theme, you know, the common theme that I want you to kind of pick up from this, that all of these applications have two fluids. Okay. Okay. And those two fluids need to exchange heat. Okay. Most of the time, a lot of the times that second fluid is air, and then the other fluid is some kind of liquid, either some kind of coolant or maybe some kind of oil, right? You know, but that's typically what it is. Okay. All right. Any questions on this? Yeah. 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 So usually you have a hot fluid. So we'll refer to the fluids as one's going to be the hot fluid and one's going to be the cold fluid, and then heat's going to flow from the hot one to the cold one. Yeah. Okay. And so let's just go over really quickly different heat exchanger geometries. Okay. And so there's lots of heat exchanger geometries out there. So, if you open up your car, you look at its radiator, you're going to see one type of geometry. If you open up your AC unit, it's going to look something different. So there's lots of different geometries out there, and it's really kind of impossible for us to kind of go over them all here. But we can go over some broad classes of geometries. And so the first geometry, and the one that we're going to be focusing on mostly for this unit, is what's known as a concentric tube heat exchanger. You'll see me use this acronym here, or this shortening, because heat exchanger is kind of a long word to write sometimes. So I'll just write out HEX, and so HEX stands for heat exchanger. Okay. And so the concentric tube heat exchanger, I would say geometrically and from an analysis standpoint, this is the simplest that you can get. Okay. And what it is basically one tube inside of a bigger tube. Okay. Okay. All right. So from I'll draw the front view first. And so from the front, right? And so if you're looking kind of straight down the tubes, it's going to look like this. And so you have a big tube here, and then you have a smaller tube in the middle. Okay. And so the way these work is that in the inner tube, you're going to have a certain type of fluid there. Okay, so this would be fluid 1. And then in the outer tube, and so we call that the annulus, or I like to call it just the donut. Okay. And so in the donut, we have fluid 2. And so fluid 2 is basically going to be surrounding fluid 1. Okay. All right, so that's the front view, but I think the one that we'll use for analysis most of the time is going to be the side view. Okay. And so let's say we have fluid 1 in the middle, and then surrounding it, we have fluid 2. All right, so that's the geometry we're going to work with the most. Mostly just because, if you look at the inner tube here, right, we basically have flow in a pipe, right? We've already covered that with internal convection, right? And so we can leverage a lot of what we've already learned about internal convection and then apply it to the inner tube. Okay. The outer flow is going to be a little bit different because it's flow in an annulus, not in a tube, but we can apply a lot of the same principles to that one as well. All right, so that's the one we're going to be focusing on a lot, although you don't see that too much nowadays. Okay. Okay. Another type of geometry that you might see is a what's called a cross flow heat exchanger. Right. So this is a common geometry when air is one of your fluids, right? And so it looks kind of like this. So you have kind of I call it like a bank of tubes. So we have a bunch of tubes lined up together. And most of these tubes are going to be mounted on basically like a big plate right here, okay? Right. But this plate is going to be slotted. And so what you're going to have is, this plate that I've connected to is thin, and then right behind it, you might have another plate, okay, that's holding holding the same, that's holding the same pipes. Okay. And so the pipes are going to go from plate to plate. And of course, the pipes are going to be carrying some kind of fluid, usually some kind of liquid. And then in between the slots, or in between the slats here, we're going to have some kind of airflow. Okay. Usually it's air, but you can have these with fluids as well. Okay. And so we'll say that fluid 1 is going to be flown almost like in cross flow, right? And so we have a fluid 1 that's going on top of the pipes. Okay. Whereas fluid 2 is going to be flowing inside the pipes. Okay. So that's why we call it cross flow. And so, you know, we're basically putting a lot of the flow into these tiny tubes, but then our other flow is going to be pushed on top of the cylinders in cross flow. Okay. Okay. This one's popular just because, you know, if you remember from our unit on external convection, we already know how to analyze a cylinder in cross flow as well as internal flow. And so this one, you can kind of mix the two together, but then you kind of multiply it by, you know, however many pipes that you have, and that gives you a cross flow heat exchanger. Okay. All right. And so the last type that we'll see, or that I'll show here, this is a common geometry for radiators. And so this is called the shell and tube heat exchanger. And so the way these work is that you have a tube, okay? And usually the tube is coiled. So it kind of snakes through a device like this, okay? And it's going to come out just like that. Okay. And so of course you're going to flow one fluid in here. So we'll call this fluid 1. Okay, so fluid 1 is going to flow through that. But on the outside of this tube, you're going to have what's called a shell, right? And so all this is going to be housed inside a unit like this. Okay. And then on the outside of this tube, oops, forgot to draw an inlet and the outlet. Okay. Outside of this tube, you're going to have the other fluid that's going to be flowing on top, right? So inside here, you're going to have fluid 2. Okay. And fluid 2 is going to kind of flow across the tubes just like that. Okay. Okay. This is a nice geometry when you're often kind of constrained for space, which is, you know, often the case. And so a lot of times, you know, these heat exchangers, they have to kind of do its work in a very small amount of space. And so this is kind of a good way to kind of maximize that space by kind of coiling that tube and then running air over the tube in a confined shell like this. Okay. All right, any questions on this before we wrap it up for this week? Okay, all right, so that's all we got time for. And so when we pick this up on Monday, we'll start doing some calculations with heat exchangers, okay? And then we'll go from there. So thank you guys for tuning in today. Hope you guys enjoy the rest of your week and your weekend, and I'll see you guys on Monday. Thanks, guys. Yeah, sure. What's your question on the homework?
Are you able to hear me like this?
I'm not sure if you're talking, Nick, but I'm turning up the volume in case you are.
Yeah, can you hear me now?
Okay, yeah, I can hear you now.
Okay. On the homework, question number 2,
Yep.
we're dealing with the pipe under the water.
Yep.
And so I assumed for part D, it wants us to find H inside. And so I assumed it's going to be constant wall temperature because we're assuming the water has the constant temperature.
Mhm.
Is that, but I just, for some reason, am not getting anything near the value that you got for H. I don't know if it's because my K is off. But
I think
just
for that one, I assume that it's a constant wall flux. Let me just double check really quick.
Okay.
I don't have it in front of me, so I need to go log on to Canvas. and check. Let me go ahead and share my screen.
Warehouse and.
Oh, no, I know, I was working where.
Okay.
Yeah, so
There's no AC.
and they literally.
You're talking 2A, right?
Yep. Or I guess 2D technically.
2D.
We didn't.
Yeah, the H.
Ah, yeah, so for this one, you can actually compute H without the mean temperature equation. And so for part D, actually, I want you to use a neutral correlation for this one.
So that's,
So- I think-
that's, okay, ahead.
Yeah, I think for this one, because the Reynolds number is so high, you have turbulent flow. And so we have a neutral correlation for turbulent internal flow that you can use to compute H for that.
Is that the one where it's like H is equal, or the Newsel number is equal to H is equal to like KF over D?
Yes,
And
yeah,
that equals, so that's the one I'm trying to use. I don't know if my K value is just really off.
yeah. So the neutral number for that one, let me see. Oops.
I think I got 3.66 is the one I was trying to use.
Let me check the handout here. Oh, I uploaded it. I just didn't see it.
I think we're doing, we might be doing.
Internal flow. Here we go. So the neutral correlation you should use is this one right here.
No.
Oh, okay.
Yeah, so you have the Reynolds number from the previous step, and so you go ahead and plug it in here, and you have the Prandtl number. And then I think in this case, the fluid's being cooled, and so you need a N of 0.3.
Got it. Okay, that makes sense.
Yeah, and then if you compute that neutral number, you can compute H from that.
Got it. Okay, then I will do that.
Okay.
All right, thank you.
Yep, no problem. Any question? Okay, 2C. 2C is the Reynolds number, right? Okay. Let's take a look. Oops.
Yeah. But I think that.
We have to assume it.
But like I said.
Right. You don't have the velocity, but I do give you this the flow rates. Yeah, you just have to divide it by the area. And so we're assuming that the flow rate here is equal to velocity multiplied by the area. And so since I give you this, you can compute the area just from the diameter and just divide it by the area. Yep. Mhm.
I got home like 2:30, 2:40.
Oh, yeah, for sure. Let me go back to my iPad here.
Yeah, you guys were still talking.
Oh, yeah, I was now.
We were like 5 minutes. You guys like last year was that surprise?
Okay.
There was the one down installed.
Yeah, so the idea of the shell and tube heat exchanger is just that you have two parts. And so you have a tube that kind of coils around just like this. And so inside that tube is some fluid. So we'll call that fluid 1. And then on the outside of that tube, we have a shell. And so inside that shell, you have kind of another fluid that kind of flows past it. And so this type of heat exchanger is you often see it in a car radiator because it's very space efficient. So you can basically cram, a heat exchanger that has a lot of effectiveness in a small area of space.
What the hell are you doing with the red wire? Don't cut the green one.
Mhm. Yep.
Yeah, so when he's doing his shit, I'll just.
We
be
probably
like,
wire some big stuff like that.
All right, Nick, Elson, any final questions?
Now we need to get the output.
No, sorry. I'm just hanging out.
Okay.
I'll help.
All right, I'll see you guys Monday then.